Okay, in this podcast we're going to talk about aqueous solutions as well as how to write net ionic equations. When you think about, let's say I have two ionic compounds, they're usually going to be crystalline solids. And if I throw them together into a beaker, nothing's going to happen because they are not mobile. And they have to be able to move in order for collisions to occur, for a reaction to occur. So once they get dissolved, now I have these ions that can move freely in this liquid, and I can have reactions. So most reactions, or an awful lot of reactions, occur in solution, and specifically they occur in aqueous solutions, which means when they're dissolved in water. Okay, so before I'm going to talk about different types of reactions that occur in solution. The first, you probably learned in honors chem that it's called double replacement. Sometimes these are called metathesis equations. And these reactions include two different types, which we often call, one is precipitate reaction, which is obviously one that creates a precipitate, and the other type of double replacement we use a lot is acid-base. Just the double replacement reactions. And that all products require some driving force. So what's a driving force? Well, a driving force is something that's a new product. In order for a reaction to occur, the definition of a reaction occurring means that something new was created, a new compound, a new element that was not there in the beginning. So we call the new product formation a driving force. Because in fact we can combine some things. For instance, if we were to combine sodium nitrate and potassium chloride, as it turns out, I end up with no reaction. I just end up with a bunch of ions here and a bunch of ions here. I mix them together, if these are aqueous, and nothing new forms. I just have ions floating around. Okay, so there are three different things that we look for, three different driving forces we look for in double replacement reactions to tell us that the reaction has occurred. So let's take them one at a time. So the first type of driving force is a precipitate. I'm just going to abbreviate it as PPT, a precipitate. So a precipitate is something that forms when two solutions are mixed. Right? It's called a precipitate. And if you watch what happens, precipitate. If you watch what happened when you take two test tubes with clear solutions and you mix them together, what you'll actually see is it starts off looking cloudy, and then that cloud will start to settle on the bottom, and eventually you'll end up with solid stuff on the bottom. That's a precipitate reaction. It's kind of like snow forming. You see this clear liquid suddenly have all these things form. You could think about them like the precipitation of snow, and they fall onto the ground and form a pile. Okay. So it happens when two aqueous solutions form a solid when mixed, and we call that solid a precipitate. So here's a typical precipitation reaction. I take potassium chloride, and if I look at potassium chloride aqueous, I have potassium ions and chloride ions floating around. I add aqueous silver nitrate, and again I have silver plus 2. Now the waters that are hydrating this, surrounding this, don't show, just for simplicity. And then I have the nitrate ions floating around. And when they mix, what happens is when the silver and the chloride collide, they are attracted to each other. And that attraction forms this solid, and we say that it's insoluble. And this is the solid that falls to the bottom of whatever container they're in. And then we're left with this potassium and the nitrate still floating around as ions like it did over here and over here. Okay, so the fact that I made a solid makes this a precipitate reaction. Now it's a solid falling out of a solution that makes it a precipitate reaction. So in order to determine whether or not you're going to make a precipitate, you have to look at your solubility rules. And here's just a simplified version of the ones that you worked on over the summer, but you need to understand them and know how to use the table. So simply, this will capture 95% of what you're going to run into. Nitrates, group 1 alkali metals, ammonium, acetates, perchlorates, and chlorates, are anything that has any of those ions in it is always soluble with no exception. Chloride, bromides, and iodides are usually soluble unless they contain lead, silver, or mercury. And the sulfates are often soluble unless they contain one of those or calcium, strontium, or barium, which lie one above the other in the periodic table. Okay? So let's take a look. Let's write what we get. So we just start up by writing the plain old reaction. We're going to have the iron and the sodium are going to swap partners, and I'm going to end up with iron and hydroxide. Now you might ask, how do I know whether I'm getting +1 or +2 iron? Well, I got to look at what the charge is here, because this nitrate is a -1 and I have 3 of them. This must be a +3. So it's going to make a +3 over here. Okay? And I also get sodium nitrate. So if you look at your solubility rules, decide whether or not that's going to be, whether these are going to be aqueous or solid. Okay, so you should have seen that this is solid and this is aqueous. Okay? If I take the aluminum sulfate and the barium chloride, I end up with aluminum chloride and barium sulfate. So pause and decide, and now I'm not balancing these equations, I am balancing what's formed. So take a pause and decide whether or not these are aqueous or solid. Okay, this is aqueous and this is solid. I have hydrogen iodide and zinc nitrate. The hydrogen is going to end up with the nitrate, +1 and -1, and the zinc is going to end up with the iodide. Okay, so, and this needs to be 2 because the iodine's a -1, zinc's +2. So this is a strong acid. Okay, so it's going to be aqueous. Strong acids are always aqueous. The zinc iodide, well, it's an iodide, it doesn't fit the exceptions, so this is also going to be aqueous. So if I look at this is going to be no reaction, because the ions I have here, I formed nothing new, because what I have here is H plus and NO3 floating around. I have zinc +2 plus I minuses floating around, but that's also what I had over here. I had H pluses and I minuses. I had Zn +2s and NO3 -1s. I've had the same thing forming. Same thing that I started with is what's formed. Okay. If I look at calcium chloride and sodium phosphate, pause it, write the reaction, decide whether you get something solid or aqueous, and then start back and see whether or not you were correct. So I'm going to end up with calcium phosphate and sodium chloride. So what you should have identified as the calcium phosphate is a solid because it's insoluble. Calcium is one of the exceptions with the phosphate. And the sodium chloride is aqueous. The lead nitrate with the potassium sulfate, I'm going to end up with lead sulfate. This is a lead 2, so it's going to be lead 2 here. And potassium nitrate. So pause. This is going to be solid. This is going to be aqueous. The last driving force we look at is a gas. We can form a gas, and the evidence of a gas is that we have bubbles that come up through the solution. And usually, I'm I'm sorry, I'm jumping ahead. I'm not ready for gas yet. I form a new molecule. And that molecule I form is often water. Water is the molecule that gets formed in an acid-base reaction. So if I take potassium hydroxide and hydrochloric acid, this is a strong base, so this is what I have. That's what I have floating around is these ions. But when they react, I end up with H2O, which does not have ions. It's floating around as a water, which is a liquid, which is a molecule, and I have KCl. So this is aqueous, but here's my evidence, my driving force that tells me this reaction occurs. Okay, so now let's talk about the driving force that's a gas. And the gas we form a gas. And what you have to recognize is there's common gases, and you need to know what all these are. So you probably recognize carbon dioxide and hydrogen and oxygen. But sulfur dioxide and sulfur trioxide are also gases. Hydrogen sulfide, the stuff that smells like rotten eggs. Nitrogen dioxide is a gas. And ammonia is a gas. And we talk about ammonia a lot. So you need to know that ammonia is NH3 and that it's a gas. So you need to know these. The other thing you have to be aware of is that you may form something in a double replacement and it looks like it's not a gas, but you have to recognize that these three substances decompose immediately into always a combination of water plus something else. So the something else is whatever is left after I remove the two H's and an O. This forms water and carbon dioxide, and the carbon dioxide is a gas. The H2SO3 forms water and SO2, which is a gas, and this forms water plus NH3, which is ammonia gas. Okay? So in all three cases, if I form these, I am also forming a gas, because that reaction is immediate, that decomposition. Okay, so let's take a look at this. I have excess HCl is added to a solution of potassium sulfite. This is where this kind of thing might show up. That's a sulfite, so I need two of those. So I get KCl, but I also get H2SO3. Okay? So I'm going to need two of those and two of those. So I look at this and I say, I didn't form a molecule, I didn't form water, did I form a gas? Well, this is on the list, right? This forms H2O plus SO2, and SO2 is a gas, so this reaction goes. Okay. So a solution of sodium hydroxide is added to a solution of ammonium chloride. So I have sodium hydroxide plus ammonium chloride. So when I react those, I get sodium chloride and ammonium hydroxide. And this ammonium hydroxide is on the list we just talked about. I'm going to get water plus ammonia. And this is a gas, so this is my driving force. Okay, we're going to stop there.